Right, folks, let's continue. Another technical topic today, but a topic that will allow you to do a lot of chemistry in the subsequent lectures and in the various other modules. Throughout your education so far at school, and perhaps quite a few subjects by now here at the university, you have come across these strange symbols. Things like F, X, and so on. You were told when you are integrating that the act of taking an integral involves expressions of this type, where you were never actually explained all that well what this dx actually means. You were told to drag it along through these expressions, and the explanation was waiting until some future date. Well, that date has come. You will also see, perhaps you have seen it already, the second year's notation in chemical kinetics, like dc by dt is minus kc, which is a differential notation. In this case, it involves the derivative of an unknown function. C is a function of time, and you're looking for it. So, what is df? What is dx? Why must we have it under the integral? Why this notation? And what do we do with this? How do we solve such equations? So we will discuss today what it actually means to be a differential, which is the name of these things. So the first topic is differentials. You may remember the definitions that we had for a derivative. It involved a limit. Our f prime of x was defined as the limit of delta x going to 0, f of x plus delta x minus f of x divided by delta x, or in shorthand it was limit delta x going to 0, delta f over delta x. So the increment in f that is caused by the change in the argument delta x divided by the change of the argument in the limit when delta x goes to 0. And we were doing various things to it. Remember the expressions that we had for the tangent line in terms of these things. And we were also doing things like getting approximate expressions for this. So if I take a finite increment instead of infinite, this will become an approximate expression. So it will be plus some correction term, x delta x. And you may remember a couple of boards that I have filled with mathematics dealing with expressions like this. They are, well, rather unpleasant and bulky, and we are not the first group of people to whom this occurred. These general considerations of infinitesimally small versus finite increments, they actually go back to ancient Greeks, who were dividing their geometric figures like cones and paraboloids into infinitesimal slices and then summing up those slices. And some of the ancient Greek philosophers were actually quite proud of having figured out the volumes of things like the cone and asked the formulas to be inscribed on their tombs and so on. So to them, this was lifetime's work, it was really complicated. Then Newton and Leibniz came about, and Newton's treatment of these matters in 1650s or thereabouts is rather convoluted. His notation is hard to read. In 1670s, Gottfried Leibniz in Germany has invented much neater notation, so it's d by dx and d by dt. And it is in fact Leibniz's notation that we are using today. So let us see what he had meant when he introduced these d's. What I will do is I will now say, okay, so with this correction term, this expression is actually exact, right? So the approximate expression for the derivative and the correction. And I will multiply this by delta x, and I will put f, this numerator in front of the equation. So what we have is f of x plus delta x minus f of x will be equal to the rest of this. So f basically a rearrangement of the expression here. I multiply both sides by delta x, so we get f prime x delta x here, phi delta x there. I shift all of that over there and just flip it around, and so what we have. Have we missed something? Yes, well spotted. And this is just delta f. So why don't we write it that way? We will have delta f is f prime of x delta x minus so what Leibniz said is, why do we bother with making them finite? And he didn't really have a concept of a limit. It appeared in a rigorous form with Cauchy much later. So Leibniz said, why don't we just treat this as infinitesimal straight away? In which case this correction would vanish because delta x is already infinitesimally small. And what we will see is df is f prime of x dx, where d is the infinitesimally small version of delta, and the correction has now vanished. And you can see this now explains Leibniz's notation. Previously, I introduced df by dx as just another way of writing the derivative, but now you can see that there's actually a deep mathematical connection between the two, that these have not the meaning of just a strange-looking solid symbol. This is genuinely something that is a ratio of two infinitesimal increments. And then we are allowed to multiply by dx and move dx around. And so we are allowed to split this symbol into the numerator and denominator and move these around the expressions. And even then, the d operator becomes an operator that corresponds to an infinitesimal increment of whether it be a function, an argument, or something like that. So now what follows is actually the properties of these differentials. So this is the fundamental one that we will be using to prove everything else. And why don't we take a look about at what the properties are. Well, the differential of a sum d f plus g, as the definition here suggests, will be f plus g prime dx if they both depend on x, which is of course then f prime dx plus g prime dx, and f prime dx is just df. df plus dg. And so it appears that the differential operator is linear. If you have a sum on this differential, that translates into a sum of differentials in much the same way as this happens for derivatives. So for our purposes, these functions are actually very closely related. And then, likewise, d of alpha f is alpha dx, that's alpha f prime dx, and that is alpha df. So you can take constants out of the differential, and together these two properties, additivity and linearity with respect to a constant, are just called linearity. But quite a few other properties follow, which we actually proved in the previous lectures at great pain. Remember, I was proving you the product rule with the limits, and again I had to use most of this entire board to drag you through the limit expressions for that. And the same went for the chain rule. In fact, the reason why this differential notation is so popular is that it is extremely powerful and compact. Let us see how long it takes us to actually prove the differential for a product. So we'll have d, f, g, and that is f, g prime dx. But f, g prime we know is f prime g plus f that is f prime dx minus g plus f g prime dx. This is df, that is dg, and so this is actually f dg plus gf. Nice and easy. And let us now take the really difficult case. Remember the appendix B from my handout that I encouraged you to look at, but not terribly carefully because it just had horrendous mathematics in there. That was for the chain rule. So if we have d f of g of x, so the nested thing, well, actually this, by the very definition, because g is an argument, that's f prime dg. But then g is in itself a function, right? So dg must be g prime x dx. So we just replace it. So this was f prime of g dg, and now this is f prime of g prime of x dx, which is literally just one line instead of a page of horrendous limit expressions. So operating with infinitesimals directly, provided you are careful to remember that this is already an infinitesimal quantity and that df squared, for example, is much smaller than df. For that reason, remember the various limits arguments. So as long as you are keeping in mind that this is already a limit and tread lightly with respect to that fact, expressions involving differentials are much smaller and much more powerful than expressions involving finite increments. To give you another example of how powerful this is, differentiation of implicit functions. For example, we have y equals f x. But what we would like actually is to know the derivative of the inverse function. Well, from here, we can say that dy dx is f prime of x. But what we would want to know is what is dx by dy. Previously, this wasn't obvious because we were given this notation as a solid symbol. But now we actually know that it is truly a ratio. And so if we flip it around, what we simply need to do is to flip the other side around. So this is 1 over f prime of x. And what is x? X is just the inverse of f. So this is 1 over f prime of f minus 1 of y. So where x here inverse function, arc cosine for a cosine, exponential for a logarithm, and such like. So actually the implicit differentiation of inverse function again became provable in just one line. So this formalism is something that we use a lot in physical chemistry, precisely because it saves a great amount of formal mathematics by already incorporating the fact that we are dealing with infinitesimal quantities into the formalism itself. Okay, now all of this looks obscure and bizarre. I fully appreciate that. It will take some getting used to. This is what the workshops are for. So it is quite important that we actually give plenty of examples here of how to calculate such things. And example 1 is to calculate just a differential of a simple function. So if we have f of x equals exponential of minus x squared over 2, simple Gaussian function. Okay, well, as per the definition here, df is f prime of x dx, and the only thing we need to do is exactly what you know how to do by now, that is to calculate the derivative. And the derivative is the exponential of minus x squared over 2, that's the outer function. and the inner function is minus x squared over 2, so basically minus just x. Because the derivative of x squared over 2 is 2x over 2, so that's just x and the minus multiplied in front, and that is here. So the final answer here is minus x and that's the differential. This is how an infinitesimal increment in the function connected to the infinitesimal increment in the argument. Roughly speaking, that's the slope of the curve. This is how steeply the function changes at each point, and we can sort of draw a geometric diagram in here. You remember how a Gaussian function looks. It's something like this. And it has a maximum at 0, and so at 0 the tangent line is horizontal. It neither grows nor drops at that instantaneous position. And predictably, if you put x equals to 0 in here, you get a 0. And that is positive growth rate here, negative growth rate there, and this minus actually does account for that. If x is negative, this becomes positive, so we have a positive growth rate. If x is positive, this becomes negative, so it's a negative growth rate. So another way of interpreting this is the differential expression is a relation between infinitesimal increments of the arguments and the function. It is the local rate of growth. Okay, so that's the first example. Let's take another example of the differentiation of the inverse function and the product rule. So starting with the product rule. 2. If we have df by dx equals cosine x, and then x itself is t cubed. In here, we don't actually know what f is. It could be quite a lot of things, because quite a lot of things have a derivative that is equal to the cosine. There's an arbitrary family of curves with the derivative that's equal to the cosine. So we're not actually even told what f is. We only know its derivative. And we know that x depends cubically on time, and we are asked to find out df by dt. Well, that's actually quite easy, because we can calculate dx, which is 3t squared dt, and therefore dt is dx over 3t squared, and therefore df by dx is df by 3t squared dt, and that was still cosine x, cosine, but x is t cubed, cosine t cubed, and then the last thing to do is to multiply this by denominator, and therefore df by dt is 3t squared cosine t. Let me see if I've got everything right here. Yes. Now, this is an extremely important instance of something called derivative translation. When you have a derivative with respect to one variable and you substitute in another variable, you can find out the derivative with respect to that variable without looking at the function itself. You will see a lot of this when we get into integration. So integration by substitution involves transformation of differentials of this type. But ultimately, as you can see, in all of this ostensible complexity, the only thing you realistically need to remember is this definition. Everything else follows. You see a differential, that's what it is. Just sub in the function, and everything will happen automatically. That having been said, this requires a lot of practice, because you have to acquire the intuition about how all of this works. You look at the formula long enough, and the answer and the possible transformations are just jumping at you You will notice, for example, that the other class tutor, Maria Grazia and Marina, you have some, difficulty or complication or some arithmetical error on a piece of A4, densely filled piece of A4. Marina will just come, take a quick glance at it, and point out the error. That is an acquired skill, and this is something that you will also eventually acquire. Professional chemists, the ability to just scan through an entire page of complicated formulas and immediately point out the error. Somehow human brain eventually adapts to doing it. Okay, so example 3, let's take an inverse function. 3, we are told that y is a sine x, but we need to calculate dx by dy. And I don't know about you, I think at some point Hannah impressed me by actually remembering the derivative of an arc sine, but I don't. And so why don't we just run this using the differentials? So we know what dy by dx is. Dx is a cosine x. Right? We all remember how to differentiate sine. Therefore, dx by dy is 1 over a cosine x. Yeah? But then we'd really like this to be a function of y, so we need to invert this. What I will do is I will say, okay, this is 1 over a, and then cosine is root 1 minus sine squared x. And then this I can then express, so we can say that y over a is sine x. Substitute that in 1 over a root 1 minus, and then that's 1 over a squared. And that, let's pull a under the root, 1 over root a squared minus y squared over a squared, but we are multiplying by a squared, so just y squared, and at that point we're done. So dx by dy is 1 over root a squared minus y squared, where you will now recognize, perhaps from encountering that in the textbook somewhere, the actual derivative of an arc sine. But we don't need to remember it because we know how to differentiate the inverse functions. Okay, so this is for univariate expressions when the function depends on only one variable. What happens when we have multiple variables? So item 3 on the agenda is differentials of multivariate functions. It actually stands to reason that infinitesimal increment with respect to variation of many variables is just the sum of increments with respect to each variable in turn. So we could go through the complicated limit expressions, but that's not actually necessary, they are trivial. So df of x, y, z, and so on is df by x plus dy plus the z part and so on. Literally just the slope with respect to x times the increment in x, slope with respect to y times the increment in y. That is, one can view it as a scalar product of the gradient vector and an infinitesimal step along or down the gradient vector. So this is again one of the greatest advantages of differential calculus in the simplicity of the expressions here. So you will be asked a lot in your chemistry courses to do this. And the principal example of that is actually chemical thermodynamics. Now, let me remind you of some fairly straightforward thermodynamic problem. If that is volume and that is pressure, for example, at some fixed temperature, and you have an expanding gas that pushes back the atmosphere and does some work. Therefore, right, P delta V, as you remember, is the work against atmospheric pressure that a particular physical system does. And let's say we are having 2 points here and here, and we are moving the system through some trajectories. And let's say in the first instance, we have first expanded the system and then we increased the pressure. So we took that path. So path number 1. And in the other instance, we have first cranked up the pressure and then increased volume. For example, that's number 2. Now, because of the conservation of energy, it is clear that the initial energy and the final energy in an isothermal process, for example, should not depend on the path that the system had taken. Energy is a function of state, and the eventual final energy of the system at this point cannot possibly be a function of how the system got there. Otherwise, you can make a perpetual motion machine. However, what is also clear here is work. Right? So the total Q, which is the integral of P dV, the amount that the system had done against the atmosphere, it expanded through exactly the same volume, but at wildly different pressures. And so the amount of work the system had done is actually different across these two paths. So at some point, because of this difference in work, we had to heat it up differently, right? For it to stay at the fixed volume and then increase the pressure, a lot of temperature must have been supplied to it. Right? In here, we simply let it expand, but we kept the pressure fixed. For the system to expand but stay at the fixed pressure, you do have to heat it up. Right? So heat has been supplied to the system in here, and so different amounts of heat versus different amounts of work would have been done. So clearly, some functions like energy, internal energy, usually we use U rather than E in thermodynamics, Gibbs free energy, Helmholtz free energy, entropy, and such, do not depend on how a system got there, but quantities like work do. Formally speaking, what this means is the functions of state, so things like du, increments in U, the increments in the Gibbs free energy, the increments in entropy, are what's called exact differentials. And then this goes back to one of the questions I think somebody asked at a class: why do we use a different delta for work? You will see that done in your textbooks, because this is not what mathematicians, or perhaps specifically physical chemists, mathematicians never use this little delta notation for inexact differentials. But let's look at the difference between them. Imagine we write down something that involves dx and dy. So something here, dx plus something else, dy plus perhaps something else here, dz, and so on. As per the definition of our differentials, df by dx must be the content of this bracket, df by dy here, df by dz here. But if we just write something arbitrary here, it may well be the case that such a function simply doesn't exist. So there isn't a function whose d by dx is this, and d by dy is this, and so on. So if such a function does exist, this is called an exact differential. And if such a function does not exist, it's called inexact. And it so happens that for the functions of state, the differentials are exact, but for work and heat isn't. So let me give you a couple of examples, because this notion is slightly weird and takes some getting used to. So I've got a couple of examples here in your handout. So it's actually example 5, and then I will explain what that means. Example 5, if we look at x squared plus y squared dx plus 2x y dy. So, does there exist such a function f for which df plus df by dx plus df by dy. So essentially, does there exist a function where df by dx is x squared plus y squared, but df by y is 2x squared? So does f exist? Well, that's a very difficult question on the surface. Goodness knows what that function is, right? It could be some horrifying polynomial that just happens to have derivatives like that, and it would be, by just intuition and staring at it, rather difficult to determine whether or not that's actually possible. However, remember what I told you ages ago about well-behaved functions. That if the function is well-behaved, polynomials and so on, then the mixed derivatives must be equal. So we must have d2f by dx dy equal to d2f by dy dx. Remember, you did a lot of such problems in one of your problem set in the workshops. You were asked to confirm that the mixed second derivatives do not depend on the order of differentiation. All right, but this is our df by dx. So if we differentiate this with respect to y, we will get df by dx dy. And if we differentiate this with respect to x, we ought to get d2f by dy dx. And if the function exists, if it's real, these two things must be equal. Why don't we check? So d2f by dx dy here, differentiated with respect to y is 2y. But here, d2f by dy dx is 2x, differentiating with respect to x, also 2y. So they're equal, so such a function does actually exist. We don't know what it is, but it does exist. And yeah, that's it. I think my example in your handout has a minus, so in that example it doesn't exist. But for this particular function that I wrote, the one with the plus, it does. If we had a minus here, this would have been minus 2y, this would have been plus 2y, and it would not have existed. Okay, so what then is the criterion for something being an exact differential? It's literally as what we've just done. So if we have g of x, y, some function, x plus h of x, y, dy, this is an exact differential. Since this must be a derivative with respect to x, we must differentiate this with respect to y, so dg by dy must be equal to dh by dx. So you have to check mixed second derivatives. And to give you an example from chemical thermodynamics for this, if we have our enthalpy, H is U plus PV, At some point, your thermodynamics people will introduce this. This is one of the functions of a state. I think suitable for isobaric ensemble, particularly convenient for it. And then the differential of that is dH is du plus p dv plus dp, just the product rule. But then from the second law of thermodynamics, we also know that du is Tds plus P. And so we can now merge these two. So you have du, we substitute with minus there. Tds minus Pdv. Handout. If we substitute that here, one instance of Pdv cancels, and so we have dH is Tds plus Bdp. Now we know that enthalpy is a function of state, and it therefore must be the exact differential. What this then does is it places constraints on the derivatives of temperature and volume with respect to these parameters. Since this must be the exact differential, then dt by dp must be equal to dv by ds, I think, yeah. And these are called Maxwell's relations. After James Clerk Maxwell, who is not only famous for electromagnetism but also for some analysis of thermodynamics, he essentially recognized that these mathematical conditions on the exact differential have physical implications. And so in any thermodynamic process happening under certain conditions under which these functions are applicable, such relations must hold. And those of you who go into industrial chemistry, who have to deal with the heat transfer and so on in chemical reactors, will have to do this rather a lot. Okay, so let me give you one last example of a multivariate differential. Let's just calculate the differential of a simple function to give an example of how it's done. So all of this on first go through it will be difficult and obscure. Do not expect to understand it straight away. I certainly didn't when I was an undergraduate. So that will involve a lot of sitting in the library and a lot of scratching of various locations before you actually become comfortable with this. So xy will be x sine y. And then our differential for this, df, as the definition somewhere there suggests, df by dx dx plus df dy. And the only thing we need to do is just to calculate those partial derivatives. df by dx is just sine y. df by dy is x cos y. And we can confirm that that's actually exact differential by differentiating these with respect to the other variable. So d from dx dy is cosine y, and df by y dx. So we need to differentiate that additionally with respect to x is also cosine y. So really, that's the process. Okay, so to summarize everything that I've told you, this strange symbol df, I needn't tell you that it occurs everywhere. And today's lecture is about what it means. It is an infinitesimal increment, a generalization of the delta, but without explicitly having the limit. The limit is implicit in it. At that point, various expressions involving finite increments drastically simplify. Various proofs involving things like product chain rule, the derivative of the inverse function, various variable substitution processes in differential expressions, derivative translation, and such like, vastly simplified. This is why Leibniz's notation is so popular in modern mathematics and physical sciences. And then you literally just use either this definition in the case of a univariate function or that definition in the case of the multivariate function. And the only thing you realistically need to do is either to calculate the full derivative there or the partial derivatives here, and everything else is just a straightforward expression rearrangement, which you will have plenty of practice with. This occurs all over the place, in particular in chemical thermodynamics, where certain functions of state, like energy, enthalpy, and entropy, do not depend on the path that the function has taken between the points, but other functions like work and heat supplied do. And it turns out mathematically that the difference between them is the functions of state are always exact differentials. However, the functions that do depend on the path taken are not exact differentials. And the way you can tell one from the other is if you look at that expression over there, and then at the definition, and then remind yourself that a well-behaved function must have a mixed set of derivatives equal. You simply check whether the content of those square brackets survive this test. You just differentiate them with respect to the other variables and make sure that in the case of a bivariate function, that the mixed second derivatives are equal. In the case of a trivariable function, the mixed third derivatives are equal, and so on for a well-behaved function, for a function of state. They must be, and if that's the case, then that function is the exact differential. It has some physical consequences, like Maxwell's relations, and calculating all these differential expressions is nothing more than just differentiation that you have already studied in great detail. So this will all come home next week when I teach you how to solve differential equations, and there everything we do will be based on these differentials. And then when we introduce formally the notion of the integral, you will see also the geometric meaning of this dx. It's the so-called volume element or area element when you are differentiating and integrating various expressions. Okay, that's a lot to take in. I'm sorry to have dragged you through, but this was absolutely essential.